All right, so let's try this lecture one more time. I think I'm just going to give a much faster version of it this time, but basically last time I think there were a couple things that confused some people, and then also I didn't actually cover projections, so I'm going to try to fix both of those this go around. So to start with the background for this lecture, we're going to need really just two things. One is just the definition of homogeneous coordinates. So this will be that x, y, z, w is equal to really any scalar multiple of the of that four-dimensional vector, but specifically the important one is the one where the final coordinate or the homogeneous coordinate is 1, which we can get by dividing off by w. And when that's the case and the last one's 1, the x, y, z places are then the actual position in the real world. So that's what we're actually going to be drawing. And then but this four-dimensional representation is going to be quite convenient. We also need to wave our hands just a little bit and recall that the three-dimensional vector pointing from point P to point Q is Q minus P. And that's pretty much the last time we're going to be doing anything with 3D points or vectors for the remainder of this lecture. We're going to do everything else in homogeneous coordinates. And this suggests that if we have this four-dimensional or homogeneous point x, y, z, 1, and we subtract two of them to form a vector, then a four-dimensional vector is x, y, z, 0. And this, you don't have to worry about whether this is true or even makes sense. It's really just going to be a useful mnemonic device for this material. So let's do change of coordinates. So I'm going to actually set up the problem this time. So here is the origin of the world, which is 0, 0, 0, and then 1 in the final spot because it's a point. And these are the axes of the world. So here's the x-axis, which is 1, 0, 0, 0 in the last spot because it's a vector, and the other two just like you'd expect. And we'll call this coordinate frame world coordinates. You know you've set it up right because if you pack it into this notation where you have x, y, z, and then the origin, you get the identity matrix, which is quite exciting, but let's not really worry about it so much for now. Okay, so now we're going to have some other point. We're going to call it t. We can think of this as a translation. We can think of it just as a point, and this is going to be the origin of a new coordinate system. And this coordinate system will have its own axes, x, y, and z. And I think that one thing that's really important to get here is that all of these quantities, that's to say the point t and the vectors x, y, and z, are defined or written down in world coordinates. So if you were to write down t in actual numbers to say where t was, that would be with respect to the world coordinate frame, or the world coordinate axis, the system. Because this red coordinate system needs to live somewhere, and it lives in world coordinates, and that's just how it's going to be. Okay, so we now have some point. The point is P. I've drawn P in red to make it clear that P is written in this new coordinate system in red, and that'll be really clear on the next slide. But generally speaking, this lecture is going to use a lot of color. If color doesn't work so well for you, shoot me an email. I can send you some other references. So the question we're going to ask is, what is P world? So remember, P is written in this new coordinate system in the red one, and P world is the same point but written in world coordinates. So that's the question we want to answer here. Okay, so let's just go through it. It's a very simple little bit of math. So consider this coordinate system or frame that I've just told you about. We're going to pack it into this 4x4 matrix. And I'm just writing it in coordinates in the middle here just so that you remember this is a 4x4 matrix. Recall that x is going to have its 3 coordinates, and then 0 because it's a vector, same for y and z, and then t is going to have its 3 coordinates, and then 1 because it's a point. So when we write it down as this matrix F, this turns out to be really convenient, and I'll show you why. So consider some point P, A, B, C, 1 in the red coordinate system, just like we drawn in the previous slide. Now we know intuitively what P world is. P world is where we start at the origin of this new coordinate system, T, and then we add on A in the x direction, B in the y direction, and C in the z direction. And this is really just the definition of what it means to be in a coordinate system, and I'm just going to kind of do it without proof. And what's really nice, okay, yeah, x, y, z, and t written in world coordinates, just so we recall. And What's nice about this is then you can rewrite it in a matrix vector equation where you have this x, y, z, t as a matrix and ABC1 as a vector. You can check the math to make sure it works, but I'm pretty sure it does. And then that's just fp. So the punchline is that p world is just f times p, where f is this matrix consisting of the axes and the origin stacked. And yeah, it's like magic. It's very dense, condensed. It's very exciting. Okay, great. So what is PB? It's a very similar deal. We have coordinate system A, we have coordinate system B. We're also gonna write down these same matrices. All points and vectors again are written in world coordinates. And let's not think about the specifics for now. We're just gonna do it with these matrices. So consider some point PA written in coordinate system A, and what do we know? From the previous slide, we know that P in world coordinates is equal to FAPA. We know the same thing about the orange coordinate system B. We haven't really said anything special about A, we just know that this fact holds. And since we have two equations with P world on the left-hand side, we can equate them. And then invert FB to get an equation for P sub B. So the punchline here is that if we have a point expressed in coordinate system A, this is the equation that lets you re-express it in coordinate system B. And the way that's actually done in the derivation is relating them through this world coordinate system that the actual coordinate system A and B are expressed in. But if you don't want kind of to think about that, you can just believe this equation in the bottom right, which is that to get PB, we first multiply PA by FA, and then, or I guess FA by PA, and then multiply FB inverse by the result. So remember the order of matrix multiplication. That's kind of, you get that wrong, this is just not going to work out. Okay, cool. So on to the final part of the lecture. This is model view projection, MVP, reading right to left. Okay, so we start again with our world coordinates. Great. We now have this object. This is going to be what we actually want to draw. The object is going to have this coordinate system we talked about before, and we're going to call this object coordinates, and we're going to say that if this 4x4 matrix I've introduced you before, we're going to give a special name. We're going to call it the model matrix. So this is the matrix that's actually bound to the model, and then it kind of tells us everything we need to know about where and how in space the actual object is oriented. Okay, now we also need a camera because we're doing graphics. It's going to be a virtual camera. The camera is going to have its own coordinate system C, and the name of the game is kind of going to be how does the object look to the camera? That's what we're going to want to draw. C is always going to be TR, where T is position and R is orientation, unless you have some really funky camera. Okay, so we have some point here on the object. It's going to be written in object coordinates, just like before. And the question I want to ask is, what is P camera? That is to say, what is the point in the coordinate system of the camera? This is going to be the first step that's required to actually draw this point, and then draw, of course, the whole object. So we can look at so we should remember back from a couple slides ago when we had this derivation, and by pattern matching on colors, we'll get that the relevant expression is P camera is C inverse M P object. Okay, so that's our final equation. Not quite, because people don't really like having inverses in their kind of big important equations, so they give it a special name. They say that C inverse is equal to V, and we'll call V the view matrix. But really, I think C is the more fundamental matrix here, or fundamental quantity. V is just kind of what's going to show up in the derivation, or show up in every equation you're going to see. Okay, great. So we now have P camera is equal to VM P object. So, and then here's this fun fact about V. It's equal to C inverse. That's probably TR. TR inverse is R inverse T inverse, and R is orthogonal because it's a rotation, so R inverse is R transpose. Don't worry about this so much. It's probably true, but it's it's a fun fact. Okay, cool. So now the final question to answer is, what is P screen? So P screen, and I'm going to give you the somewhat simplified version here. So this is going to be, where's the actual point on the screen that we're going to draw? From the simplified version, the extension to the actual version that's used in OpenGL, or at least an older OpenGL, is quite straightforward. And I think that this derivation is probably the right one to see first, and will kind of give you really the ingredients you need to understand how projections work. It's also important to say that I'm going to define something called a projection matrix. You can have a lot of different kinds of projection matrices. So this is really, you can think of it just as a simple projection matrix. Okay, so here's the setup. We have this point in orange. This is P in camera coordinates. So we've already done the last step. And we have some camera. The camera, by convention, is going to have its z-axis pointing out at the back. This tends to be a reasonable convention. You don't need to do it, but you'll see kind of why maybe it makes some sense. We also have here our screen or our film plane. It's going to have its own coordinate system here with x and y axes, as you'd expect. And these are what are called normalized device coordinates. Essentially, this is just your screen. So what we're going to do is we're going to shoot a ray from the point in camera coordinates, or really just this point. It's in the same space regardless of the coordinate system. We're going to shoot a ray into the camera and look at where it intersects the film plane. And here I'm just looking at it, just looking at the y-axis. For simplicity, the derivation in x is going to be exactly the same, so it's perfectly fine to just look in 2 dimensions. So just imagine this is a side view. You could also look from top down, and then you'd have the derivation in x. So we shoot this ray, and now we're going to do a little bit of a game with similar triangles. So, okay, let's call d the distance from the camera aperture to the film plane. Y is the height in yellow. Negative z is the position of the orange point in the orange coordinate frame, and y is orange y is the height. So these are 2 similar triangles. We can set their ratios equal to each other, and we get this equation. And here, okay, I'm really relying heavily on color. You could do this all with subscripts, but I think it's a lot harder for slides. So we're just gonna just go with this being fine. Okay, so y over yellow y over d is equal to orange y over negative z. So you can see that, just similar triangles. Great. So now that we have this equation, we can of course solve for yellow y, which is the height of the point in screen coordinates. So this is exactly where the projection of that point intersects the film plane. Now I told you that we were just looking at y. The exact same derivation will hold in x, so here's the exact same equation, but with the y's replaced with x's. Now we need to know where we are in z. For the purposes of this lecture, let's say we're at 0. That's really where the projection of the point is. It's right on the plane, and z is the coordinate, is the axis normal to that plane. So let's go ahead and say z is 0. There are a bunch of reasons why you wouldn't actually want to pick z equal to 0. If you actually kind of leave it as the distance or some scaled version of the distance, then you can sort things and tell what's in front of what. But for here, let's just say it's 0, and then just know that you can pick other things. And this is a point, so w is going to be 1. So packing it all together, this is the position of this yellow point, the final projected point. This is what we're going to draw. So at this point, we really honestly could be done. This is the answer. But these derivations are always really hyping this idea of doing everything with matrices, and it is kind of nice. So the final step of this derivation is really to write the right-hand side as this matrix equation. And here you can see kind of the main reason that we've been using homogeneous coordinates, or I guess the second main reason, except for the being able to write translations as matrices. So here we go. Okay, so what we're going to do first is divide off by this negative yellow d over orange z factor. And this gives us the equation orange x, orange y, 0, negative orange z over d. And this is the exact same point. Remember that in homogeneous coordinates you can scale by any multiple except really 0, and you'll have the exact same point. So that's all good. And this we can actually write as a matrix equation. So in yellow here is the matrix, and that'll give, and this multiplied by orange x, y, z, p. And so this is exactly the form we would want if we were going to do a matrix equation, which is what we're going to do. And wait a second, these 2 slides. Oh yeah, okay, fine. And this slide is just putting everything together. Okay, so writing it as one big equation. So yellow point P is equal to this magic matrix times orange point P. And so this matrix is what we're going to call our projection matrix. It's just a projection matrix. It's the one that I showed you here. There's plenty of them. The main this is kind of the simplest perspective projection. There's also orthographic projections, which you can look into. They're more used for computer-aided design for engineering. And so essentially we're done, which is just to write it back in kind of our abstracted variables. So what we had right on that screen was P screen is equal to big P, the projection matrix, times P camera, or putting the entire thing together, P screen is equal to PVM times P object. So this is how you go from the actual position of the object, the actual point in the coordinate system of the object, to the point that you're actually going to draw on your screen, more or less, and that is essentially the fundamental equation of graphics, I guess. So there you go. That was that's it.